Hey guys, let's talk about alpha decay. So with alpha decay, what happens is when an atom gets too big, it's just not happy with itself. It's like, oh, I don't want to be too big. So sometimes what happens is that it spits out two protons and two neutrons bound together. This is called an alpha particle. So again, we say when it really gets too big that it's unstable and it begins to fall apart. Small atoms, by the way, too, can also undergo alpha decay if they don't have the right balance of protons and neutrons together. So an alpha particle, it's two protons right here and two neutrons right here stuck together. There's a couple different ways we also symbolize this. Often we use the Greek letter alpha, that's a lowercase alpha, it's basically an A. Or sometimes, since it's two protons and two neutrons, that is basically a helium nucleus. So often we write it like this too, He for helium, the 2 down here stands for the protons, and the 4 here stands for the total number of things there together, nucleons, neutrons and protons together. So let's talk about a few different ways that we can get alpha particle reactions. Let me clear this out of here. So let's bring up an example here. So let's say we have this chemical symbol here. So this is protactinium here. And we have this number down here, 91, and this number up here, 234. So remember some things about these numbers. So this number down at the bottom here, this 91, remember that's the atomic number. And what it means is it's the number of protons. So 91 is protactinium's atomic number, but it's also the number of protons. This number up top here, remember that's called the mass number, and it's the number of protons and neutrons together. So we'll have to keep that in mind as we go through some of these examples here of nuclei, which is the plural of nucleus, undergoing alpha decay. So let's do an example. I'll put it here so that we can write it down. And let's say that we've got protactinium that we just talked about. So we'll start writing like this. So Pa here for protactinium, 234 is the mass number, and 91 is the atomic number there. And we use this arrow to indicate it's going to undergo, that is, a change. It's going to decay. And in this case, it's alpha decay. So we've mentioned that we can symbolize alpha particles with an He and a 2 down here for the 2 protons and a 4 here for there being 4 things overall, 2 protons and 2 neutrons together. Now here's the thing. In alpha decay, you can't destroy any protons or neutrons. They all got to be accounted for. So where can we find the other ones? Well, we create a new element that's left over. So here we had 234 protons and neutrons. 4 of them are here in the alpha particle. So 230 of them have to be somewhere else, right? 234 minus 4 is 230. Now let's do the same thing for the protons. Here we had 91 protons. 2 of them flew out in the alpha particle. So that means that we must have 89 of them left over in our new thing. But 89 means we can't be protactinium anymore because we define protactinium as having 91 protons. So we got to get out our periodic table and we got to look up who has atomic number 89. Who has 89 protons? And that's actinium, right? Protactinium and actinium. The symbol for actinium is AC. And so that is what we have produced here. So this leads us to a few rules with alpha decay. So let's go over them. These are the alpha decay rules. So rule number 1 is that the mass number goes down by 4. So 234 here, down to 230. And why is that? Because 4 things were spit out. 2 protons and 2 neutrons. So the mass number always goes down by 4. The second rule of alpha decay is that the atomic number goes down by 2. And that's because we spit out 2 protons. So we were at 91 and we jumped down to 89 there. So those are the 2 rules to keep in mind with alpha decay. So let's do another example, keeping those rules in mind. Now, sometimes, especially once we learn other types of decay, they may show you what you already had in the end and ask you what the particle is. So let's say this. You see this written down. This is Neptunium, by the way. It's atomic number 93. And let's say this isotope has a mass number of 237. And it undergoes decay. And so you see this written 233 for the mass number, and Pa, which remember is protactinium, and 91. So what must the other thing be? Again, we're only talking about alpha particles here, so it may seem obvious, but we're about to learn a second type. So how could you tell what type of decay this is? Well, you would look and see we went from 237 to 233. So we must have 4 more nucleons somewhere else. Remember, a nucleon is a proton or a neutron. And our atomic number, our number of protons, went down from 93 to 91. So those other 2 must be somewhere else. And so that would let us know, if we weren't sure before, that we have alpha decay. By the way, sometimes you also see this written like this. Some books will write the symbol for alpha and a 4 and a 2. So you'll either see the HE with a 4 and a 2 or the alpha symbol with a 4 and 2. Either one's okay. All right, let's do another example where we know what we started with and we know that it's alpha decay. So let's say you see this on a worksheet. You see PO here, which is polonium. And so we get to 216 here and 84 here. And let's say they indicate that it goes to something, plus they already show you over here that we've got an alpha particle spitting out. So if that's the case, then what is the other element that's now left over? Well, we can see here, we know we always lose 4. So that means we've got to have 212 here, because 216 minus 4 is 212. And likewise here, 84, we know we lost 2, so now our atomic number is down to 82. So now we got to look up in our periodic table, what's atomic number 82? And atomic number 82 is lead. So we'll write that down. Pb is the symbol for lead, because plumbic is the Latin word for lead there. And so now we have completed our nuclear reaction. Let's do one more example here. Let's say we have one where they gave us what we wound up with and wanted to know what we began with. So let's say we see this. We see that we've got some type of decay, and again, they tell us that we have alpha decay because we see an alpha particle spit out there. And they also tell us we wound up with this. 218 is the mass number, and 86 is the atomic number, which is radon. So radon has 86 protons in it. So what was over here? What could have given us an alpha particle and radon left over? Well, now let's work backwards. 2 protons here, 86 here, so we must have began with 88 protons. Let's do the mass number. 4 protons and neutrons here, 218 protons and neutrons here, so we must have began with 222 as our mass number. So what we have to do is look up 88 on our periodic table, and we'll see that it is radium, similar word to radon. And so now we can write Ra as our final element there.